To introduce Professor Tadmor from Maryland, and his talk is on kinetic description and connectivity of old and new modeling in flocking.
Good morning. First of all, let me thank the organizers. Where are they? I don't know. And okay, Jose is not here. I'll remember that. And also, really to thank them for organizing a fantastic meeting. As you know, this week it was announced that Cambridge moved up in the ranking to #1. Maybe this conference contributed something to that. Okay, so I would like to talk about flocking. And the talk is about basically cell-driven dynamics that gives us this kind of patterns. And the question to be asked in this talk are the following one. What we see in these images are the emergence of a spatio-temporal coordination. Again, I emphasize this is a self-driven dynamics. And in some cases, there is particular attractive phenomena of phase transition, which I will not talk about. And there are many examples for this kind of self-driven dynamics. The canonical examples are, of course, flocking of birds, schooling of fish, swarming of bacteria. There were several texts along these lines, and traffic flow of army of ants. In my talk, I will try to criticize many of these models as being inadequate to describe what we feel should be a right model to describe this rather complex phenomena. But these are not just from the biological world that we bring these examples. There are the mobile and human networks. For example, I like very much the example of gossiping. It also falls into this category. And the issue is the issues to be asked are very classical. First, we want to go from some notion of elementary interaction where every bird, quote unquote, tries to fit itself into the crowd, and then we get a macro description that we saw in the first slide. And these systems are complex in the sense that we would like to understand how we observe the macroscopic description, and from this to deduce what should be the underlying phenomenological interactions. The dynamics of interacting particles or birds will include or may not include leaders, but there are three major components in this kind of dynamics, the components that drive the dynamics. I will discuss only one. There is a short and mid-range directional alignment. So basically, most of the talk is about cell-driven dynamics, where every particle tries to align itself with the group, at least with its local neighborhood. There is a short-range repulsion to avoid crowding, which is very important, and I will not discuss it because I do not know how to analyze that. And then there is a cohesion due to long-range attraction, which I will not discuss because I do not know how to analyze that. So more or less, this is the background. And there are several experts in the crowd. I try to make this talk self-contained, so please excuse me. I will start at the beginning with a few canonical examples. And the first canonical example is a model due to Vishek from 1995. The phase space consists of the location of particles. There are n particles, and their orientation, not their velocity, just the orientation. So it is assumed, this is the meaning of this overline, that the velocity field is on the unit sphere. In fact, it is assumed that all these particles have the same speed s. The only question is, what is the orientation? And the idea is that they move according to the velocity, which is dictated here for a time step delta t. And then every particle, every bird, would like to align itself with the neighbors. And this is the alignment that is written here. We look at our neighboring birds, all those which are located at xj, say in the immediate neighborhood with distance rho. And then we take an average of their orientation. We normalize it to the unit sphere, and this will be our orientation. So in this model, the Vishek model, there are three parameters: the distance rho, the speed s, and eta is the variation of the noise. Where did I put that? Here it is. And in this parameter space, it was observed in the paper. This is a canonical, this is taken from the paper. You can see here the example of phase transition. And there are many people in the crowd that are actually working on this kind of model, so I will mention later on. In this context, I will refer about Vishek model to Pierre de Gaulle. So this is model number 1, the Vishek model. Model number 2 is of Kazin from 2002. It doesn't have to do with birds. It has to do, reading his papers, mostly with ants. I will not dwell too much on this model again, just to give you the feeling of what's going on there. Again, we have n particles located at xi with orientation v bar I, and the idea is they move with a canonical speed s. Notice, and this is something very interesting here, the dynamics here is non-isotropic. It's the first time that we see that we limit the orientation to a wedge, which is very reasonable because we do not have 360 degrees vision. So this is the meaning of this red part, and that's the only thing I wanted to pick up from this Kazin model. This is number 1. And number 2, which is very important in the Kazin model, is avoidance. It's not only that we try to orient ourselves to our immediate neighbors, but if they are too close, in fact, we're trying to get away from them. So if they are too close, we're trying to get away from them. This is the avoidance. If they are not too close but not too far, then we try to align ourselves with them. I will avoid avoidance because I do not know how to analyze that. And in fact, I will rush into the third and the main model of this talk, which is slightly different. It's a semi-discrete model of Cocker and Smale. In some sense, it's simpler. Again, we have n particles located at xi. Now we are not talking about orientation. We are talking about the velocity field, vi. And the model is extremely simple. We just move with the given speed of particle I, and we adapt, we align ourselves with the velocities of our neighbors. And this is the statement that is written here. So I'm particle number I. I'm looking at all my neighbors, all of them. They are located at xj, and I'm trying to align my velocity with theirs. And the critical thing is their influence on me. This is dictated in these phi ij's. And idea is that the multiparticle, it should be quote unquote, there is no interaction, there is an influence here. Interaction is through biparticle alignment. So the phi ij is a decreasing function of the distance. The further you are away from me, your influence about my alignment decreases, and the closer particles or birds have greater influence on my velocity. And a typical example would be this kind of function R, which is it behaves like there is a polynomial decay of order 2 beta, and it amounts basically to this influence function, which should enter here. These are the phi ij. So this is a very simple system of ODEs where every particle tries to adjust itself to the neighbors, all of them, and the idea is to understand the self-driven dynamics in this case. Well, there are many things that are not considered at this stage. We would like to understand the clustering. I'm not talking about here having leaders. Clearly, they do not. This spec does not move just by itself. It has leaders. It has noise, which is another important factor which I completely ignore. I would just like to understand the essence of the dynamics behind these self-driven particles. And here it is, the self-alignment in the Cocker-Smale model. We look at this. So this will be the one slide that I will elaborate on the computations. The first thing that we notice is that there is a conservation of the total momentum. If we just sum this equation, notice that since phi ij are symmetric, the way I'm influenced by you is the same way that you are influenced by me. That's an absolutely essential feature in this model. Then if we sum it, it's 0. It means that we have the conservation of momentum, and v bar is therefore conserved in time, which basically means that the center of mass just moves linearly in time, which will be denoted by x bar. So we should view it just as a pack of birds which moves linearly in time, and the idea is, do they flock? In order to see whether or not there is a flocking phenomena, we would like to measure the energy fluctuation. That is the sum of the velocities and their fluctuation from this average velocity v bar. If we look at this quantity, and let's go along these details because they are important at this stage. So we basically take this equation and we multiply by VI, and we just sum by parts and hope for the best. So when we take this inner product, notice that by symmetry, this quantity is the negative sign of this positive amount, just by exchanging indices. Again, a critical issue here is using the symmetry of the influence function. And once this is negative, well, we would like to pull out phi, which would be, of course, the minimal value of all the phi ij's, so that we can end up with a Gronwall inequality. If we end up with a Gronwall inequality, we would like to show that the fluctuation, of course, converge to zero. That is, we do have flocking. And therefore, we have to assume that the biparticle interaction, that is the integral of phi t, I remind you what phi t is, it's written here, this goes to infinity, because it's the exponent of this quantity that will come as the total amount of impact on the energy fluctuation. So the question now is, and we still do not know whether it is true, because this still involves the dynamics, this involves the particles at time s, and we have to integrate the minimal amount of influence between the different particles. So if this quantity tends to infinity as t tends to infinity, then we know that we have flocking. The question is it true? So what will be flocking, just for the sake of this discussion? We are talking about a collection of birds such that the distance between the i's and the j element is bounded, so we can talk about a specific flock, and we want their velocities to be aligned in certain direction, which must be the average velocity. So this happens, as we just saw, if the integral of phi diverges. Well, if this happens, then of course all the velocity will be approximately v bar, which means that all the location will be approximately moving linearly along the center of mass, which means that, I remind you what phi is the minimal amount of interaction, influence between the different particles. But if all the xi's and the xj's behave linearly around the center of mass, it means that this minimum dominated the influence function r at time t, and we conclude that this integral tends to infinity, implies that the integral of r tends to infinity, and by what I'm telling you, it goes also the other way around. So now we end up with a statement that if the influence function, independent of the dynamics, decays slowly enough so that its integral tends to infinity, then we get flocking. And the summary in this case, let's take our example when we have a decay of order 2 beta. If beta is less than 1/2, we do have flocking. If beta is greater than 1/2, there is no flocking. And if beta equals 1/2, it's a borderline, a critical case. There is a conditional flocking depending on the initial amplitude. That's the end of the story. So what we really want in this model is that there is an influence which is sufficiently strong so that the decay of the influence is sufficiently slow so that I'm influenced by everybody else, even if they are far away, in a non-integrable manner. Then and only then we get a flocking in this simple Cocker-Smell model. And sure.
When all the particles, when they all have the same speed, doesn't the distance between them stay constant?
Yeah, then the distance, I will talk about that. Yes. So what happens then? You improve, you self-improve. Basically, it's not that the diameter of this flock grows. In fact, it stays constant. You're right. It stays constant. But I do not get into that, and this was done. But since you mentioned that, let me briefly talk about this issue was addressed by several people. So first of all, it was addressed by Cocker and Smale by different methods. By Cocker and Smale, they studied the so-called Fiedler number of this matrix. The Fiedler number is the second eigenvalue of a given matrix, because the first one is just about consistency. The argument that I showed you here, which is an L2 approach, is due to Ha and myself. We basically showed that the energy fluctuation decay, and the idea is exactly to find out that the decay is sufficiently fast. A different approach by Ha and Zhangwen Liu, who is not here, just left, is basically they embedded and they found a Lyapunov functional for this problem, which is given specifically here. So these two quantities are Lyapunov functionals, dissipative Lyapunov functionals, and still a different approach by Carrillo, now is here, And the other authors, some of them are here, is an L infinity approach, which is sharper. And in the L infinity approach, they do not measure just the L2 variation, they measure the maximal velocity, and they are able to show that indeed the diameter stays fixed, and then from that they get a whole series of other results. The bottom line in all these cases is that you have to have the influence function sufficiently strong so that it decays sufficiently slow so that it's not integrable. Then and only then you get the phenomena of flocking in this model of Cocker-Smale. The next three slides, so I think of this Cocker-Smale model. I mean, I learned a lot from it, in particular since I criticize it so much. I mean, I will try to convince you that if you think about it, I mean, there are many things that this model misses, and that's what I like in this business. So number one is about the Cocker-Smale is a global model. I did not limit myself to see what happens just with the immediate neighborhood. Everybody should influence everybody else. Completely non-realistic. Why? Because if we want this integral to be infinite, in particular, we exclude the possibility that the influence function will have compact support. So we have to be influenced by everybody else. In particular, if you think about a Vishek-like model, where the phi ij are basically the characteristic function times of a ball of radius r, this is excluded. So the Vishek model is not included here. And you would like to talk about a local model. What would be a reasonable local model? A reasonable local model will be the following. I will look just at the n particle I. The ni neighborhood of me, namely all the particles such that the influence is greater than 0, assuming that R has compact support. I cannot be influenced forever. So let's look at this neighborhood. Let's assume that the number of particles that may influence me, which changes in time, is capital N I. Then a more faithful model would be, of course, that the rate of change of my velocity is influenced by the immediate neighborhood script Ni. Now let's take this model and we ask whether or not we have flocking. The immediate answer is no, because let's assume that we are so dispersed that I'm not influenced by anyone. Then there will be no flocking. So in order to have flocking, we have to look at the graph of all the indices ij's, the locations xij's, such that the influence, let's say the level set is above a certain cutoff C, and we have to make sure that this graph is connected. If this graph will consist of, say, two disconnected subgraphs, I mean, there is no chance that they will interact, unless the dynamics will be such that they will approach each other. So the statement will be that if the graph is connected, then flocking occurs in this case. But is it true that the graph stays connected? This is an open question which I don't know. And to my personal taste, this is really a deep question, much deeper than all the other questions which I know how to answer because they involve PDEs. This involves a graph which dynamically changes together with the model. I do not know how to address that. So this is critique number one of a global model, a Cocker-Smale model. Let me move to some simpler questions. Critique number two. The state space is not isotropic. And by this I mean, first of all, if we are talking about biological items, birds, the most important thing is we all have vision. So, for example, let's take this model. This is a Cocker-Smale, and I would like to modify this. And I will say the following thing. If I'm particle I can be influenced only by those particles which I see. And I see in a certain a cone, which is given here with opening theta. So this again would be my immediate neighborhood. It's not local, but it's not isotropic. So this is the neighborhood Ni. And now I would like to, of course, to set phi ij as this influence function, decaying with distance, but limited to the cone of vision. So this seems like a very simple change, but is very fundamental, because now the influence function is not symmetric, which was absolutely critical in all the derivations, not just ours, in all the derivations of all the other people. So all the previous techniques do not work in this case, rather simple case, where we limit ourselves to have vision. And this is important. And therefore the Cocker-Smale model did not intend, but it does not really describe the dynamics of birds. Yes, Pierre.
If you have isotropic gamma, but
previous slide, I think the file is not symmetric either. You do not need the vision to make the...
Yes, I agree with you. It's different kind of critiques. You're right. This is not symmetric, I agree. And this is not symmetric for a different reason. So this is not symmetric because lack of connectivity, and this is a much deeper question which I do not know how to address. I just bring it up here so that people can think of it. This question is different type of lack of symmetry, which I will address in a minute, because it has nothing to do with a discrete graph. It has to do with the lack of symmetry. Now you can say, well, I've learned that actually the dynamics of fish, school of fish can sense 360 degrees, unlike our vision. But even if you take a non-biological examples, let's say like gossiping, you know that when we gossip and the information propagates, actually it's not isotropic. We somehow tend to, to have leaders. We gossip with other people. That's of course a different kind of vision you need for that. And again, you lack symmetry, and therefore the model does not apply. So this is critique number 2. Critique number 3 is that the state space is not homogeneous, and it is here that I come to a new model. What do I mean? What can go wrong with this kind of model of Kracker-Smale that they did not intend? I'm just using it as a tool in order to think about, together with you, about this problem. So here's a simple argument that I will try to convince you why the homogeneous approach does not work. So let's assume that we have local alignment. So I'm particle number I, and I'm influenced just by immediate neighborhood. There is nothing else, in fact. There are n1 birds around me, and of course I'm trying to adjust my velocity to the average velocity. So n1 is the immediate neighborhood, and there is nothing else. Everything, the space is empty. Then somewhere far away up in the sky, all of a sudden, there is a huge flock of birds with n2 birds. And of course, once they appear far away, they have to influence me because this is a global model. And they influence me in this manner. So this is what happens in my immediate neighborhood, and this is what happens really far, far away. But according to the model, we have to divide by n, which is the sum of n1 plus n2. So now we have this capital N flocking birds, which is of course wrong if n2 is much larger than n1. Because what will happen is, if far away we have n2, which is really much larger than n1, all of them will influence what happens in the immediate neighborhood. You can immediately feel that we have to give more weight to what's going on in the immediate neighborhood and completely disregard what happens in the distance. So the space cannot be homogeneous. And this brings me to the fourth model, which is a joint work with Sebastian Mauch. And the idea is this: the new model is very simple. We do not just take the influence function Rxi minus xj, but we normalize it by the relative distance. So if there are birds which are close to me, so this would be large because the distance will be small. This has much more influence on me than this huge flock of birds which is on the edge of the universe, and it will have a minimal influence because this will will measure the relative distance. So the question is, of course, what happens with this model? Well, in this model, we have basically a biparticle influence function, phi ij, which is given here. Unfortunately, it is not symmetric. And this is about time to address this fundamental issue. Can we analyze this model with non-symmetric influence function? And the answer is yes, we can. And it turns out that flocking occurs in this model and other models which are non-symmetric if the local interaction dominates the mean. So here's the condition, and under this condition, if this condition holds, then there is a general statement which says that then we get flocking. So first of all, what is the meaning of this condition? You know, in the United States at least, everybody is above average. So this condition tells you not everybody could be above average. However, if everybody is above a fraction of the average, then you get flocking, and this is basically a L2 approach. So this is the condition. Now the question, of course, is when this above average condition holds, and surprisingly, it turns out that this condition in this model holds precisely when the influence function decays sufficiently slow. So again, we cannot deal with the case of having a local support, but at least this is a more realistic model, I feel, to describe the fact that the space is not homogeneous. What I see is not what you see, the rest of the space. So from here on, so this is the end of the story about the discrete models. And from here on, I will continue with the kinetic model and then the hydrodynamic models. And I will toggle between the Cocker-Smale model, and I will mention a few things about this kind of new model, which I feel is more realistic model. So these are the particle models we want now, and this is joint work with S.Y. Ha. We would like to move now from the particle model to the kinetic description. And let's do it. So this is the phase space. We have many particles. N is large enough to observe the distribution function. And as we shall see later on, already thinking in terms of statistical mechanics is exactly, this is a very weak point, to assume that we have sufficiently many birds so we can talk about the distribution function f. But let's continue with that. So there is a distribution function f, and it satisfies this kind of Liouville equation. And we now assume that there is a hierarchy of interactions here, where this distribution, depending on xi and vi, basically can be written as this kind of product. And under this assumption, we basically prefer the biparticle interactions, which at the end brings us to a Vlasov mean field model as n tends to infinity, which is written here. So the distribution function for the probability at location x, velocity v, and time t is governed by this kind of Vlasov model. And the important thing is, of course, the local quadratic interaction, which is preferred over all other interactions. And it's given here. It's very simple. This is the linear term, and this is our inference function, which plays the critical role. So I assume here that this is the original Cocker-Smale model. And let me just mention, continuing with the kinetic description of flocking, if you add noise, you get also dissipative terms. So the Cocker-Smale model gives us this quadratic term, which looks like that. Formally, the new flocking model will give us a different kind of interaction, which I will denote by phi x and y, to emphasize that it is not symmetric. Namely, phi xy is not phi y x, given here, formally. There are also kinetic models that worked out by Degon and Moch for the Vishek model, and it's given here. And as much as I know, there is no kinetic model for the cousin model, that I mentioned before about ants. So we have this kind of kinetic descriptions, and what I want to show you how ideas from the discrete case propagates into the kinetic description, and in particular, we would like to understand the phenomena of self-ordering, self-alignment. And for that, let's continue now with this general description here. First of all, this kind of model has global existence. I'm talking specifically about the Cocker-Smale model. And immediately we observe the conservation laws from this model, the conservation laws of the total mass and the total momentum in the model of Cocker-Smale, which is not true in the new non-homogeneous model. So in the non-homogeneous model, the total momentum is not conserved. Just you can see from here that if phi is not symmetric in x and y, when you take the moment with respect to v, you do not conserve the total momentum. So there is definitely bifurcation in what we should be able to do. At least, so let me do the easy pass, and I will from now on really concentrate on the Cocker-Smale. But everything I say on Cocker-Smale could be worked out in a different way on this new non-homogeneous, non-symmetric model. So we have now a conservation of the total mass and the total momentum, and we would like to look at the energy dissipation, which is here. So this is the usual energy. This means averaging with respect to x and v. This is the usual energy, and immediately we see that the rate of change of the total energy is negative when we integrate this kind of model. However, by Cauchy-Schwarz, we see that the energy always dominates the total momentum squared divided by the total mass. So this is not the usual phenomena of dissipation. There is some sort of saturation, energy decays, and then it has to saturate into certain situation. And indeed, alignment, I claim, introduces a different kind of mechanism of bringing the global situation into some sort of equilibrium, but it's different than dissipation or relaxation. We see it again and again in the discrete model, in the kinetic model, and in the macroscopic model. So how does this kind of self-alignment brings this model into some sort of equilibrium? what we have to look is at the energy fluctuation. Again, the same kind of quantity we had before, just we have to understand what is the right quantity. In this case, it's the variation of the kinetic velocity around the mean macroscopic velocity u bar, which is m1 over m0, the total momentum divided by the total mass. This is in the case that we have symmetry, because in the case that we do not have symmetry, the total momentum is not conserved in time. We need a different machinery in order to find out what is going on there. So I'm taking here the easy road. So we look at the energy fluctuation, and indeed we see that the rate at which this energy fluctuation dissipates, decays, is given precisely by this quantity. And just like before, what we really want to do is to take this inference function outside, and we will end up with the Gronwell inequality. But in order to take this r outside, we have to measure the minimal value of r at the distance, and this will not yield flocking because we do not know whether x and y stays within a bounded domain. So we define phi t to be the minimal value of the inference function between 2 points x and y in the domain omega t, where the domain omega t is the domain of all the points where the distribution function is different from 0. And of course, this is the width of this domain that better stay finite, so we can estimate the minimal value of the inference function. And just as before, if phi t denotes this minimal value, then we end up with Gronwell inequality, and we conclude that there is flocking, that is, all the velocities go to u bar if we integrate this minimal value and it is infinity. And just as before, we have to convert this integral of phi into the integral of r, because this integral includes information about the dynamics. Phi of s is the minimal value of r, and this x now, this x and y belongs to a domain which depends on time,